First of all, let me start by thanking all of you and also especially the organizers for this really nice workshop. And yeah, for giving me opportunity to speak here today. As you see, I'm going to speak about the role of the long-range interactions in ion atom-atom three-body recombinations. And this work is part of a joint project with Jesus Perez Rios group in the Fritz Haber Institute and also recently in Stony Brook University. For introduction, I think in these 3 days you heard a lot about three-body recombination and its importance or why it's annoying for cold temperatures. I skipped that, but instead of that, I will tell you a bit about some examples in other areas of physics that's like higher temperatures that we are also doing that ones in our group. For example, we had a recent study of formation of ozone through this three-body recombination. It was a joint collaboration with Slava Kokolo and Vladimir Teterev. And we could calculate these reaction rates like in the temperature interval of 100 Kelvin to 900 Kelvin in really good accordance with the experimental available data. The other example that's like an ongoing project with Miruna Tretu from Imperial is a three-body combination of hydrogen with hydrogen plus or deuterium plus in the temperatures relevant for cold plasmas, which is like 10,000 Kelvin temperature actually. And the other example is, which is coming to more like colder temperatures, is formation of the van der Waals molecules in the temperatures relevant for buffer gas cell experiments. And we somehow predicted that it's possible to see these really weak bonded molecules in the temperatures like that people are using for buffer gas cooling. And what I'm going to speak about it today is what that you all know much better than me, is about ion atom-atom three-body recombinations in the hybrid ion atom systems. But the only thing I want to say is like I will consider both channels, forming the molecular ion and also like neutral molecules. And this is like maybe it's just the only difference. Okay, this is a theory talk. I will start with introducing the method. We basically consider this three-particle system in a Jacobi coordinate, which are shown here by these red vectors, ρ1, ρ2, and ρcm, center of mass vector. They are related to the position vectors in Cartesian coordinate with these relations. And we are going to assume that our potential is sum over the two-body potentials. And for the temperatures that I'm going to show here, this is a okay, I mean, it's debatable, but at least for things that I'm going to speak about today, this is an acceptable assumption. And finally, with all these, we can write our Hamiltonian in the center of mass frame, but here this P1 and P2 are conjugated momenta of the Jacobi vectors ρ1 and ρ2, and these reduced masses can be defined by these formulas. The method we are using is a classical method. It's classical trajectory method in hyperspherical coordinate, and is a direct method. We don't consider this a two-step mechanisms. We do like direct three-body recombination. And the basic of our method is like we map the degrees of freedom of these three particles in the three-dimensional space onto the scattering problem of single particle in six-dimensional space. Like we go from 3 in 3 dimension to 1 in 6 dimension. And we choose this six-dimensional space to be a hyperspherical coordinate with hyperradius rho and 5 hyperangles alpha 1 to alpha 5. Then we define our position and momentum vectors, like 60 vectors, using the Jacobi coordinates. And this and the P1 and P2 are the momentas, and this mu is the three-body reduced mass. And finally, you can write the Hamiltonian of this single particle in six-dimensional space with this familiar form for the Hamiltonian that we are used to. Here you see a kind of a schematic representation of our method. We first choose the initial condition, which are the collision energy or like the momentum and impact parameter B. In this six-dimensional space, we do like Monte Carlo sampling and things. And then we transfer this initial condition to the regular 3D space. We solve the Hamilton equation and then transfer back this solution to the six-dimensional space, where we can calculate the three-body cross-section basically in this radial simple form. And here this Kelly P is the opacity function, which is the probability of formation of molecule as a function of collision energy and the impact parameter. And then finally, we can calculate the three-body recombination rates, like as energy dependence, and also with appropriate Maxwell-Boltzmann distribution, we can also calculate the temperature dependence. Okay. As I said, I'm going to speak about long-range interactions. unlike the talks in the morning, our long range is still 1 over R4 for the neutral charge particle and 1 over R6 for neutral particles. Okay, this is what we have in 3D space. I was speaking about this 6-dimensional space. Then we should also map this to this 6-dimensional space. Basically, we want to find one long-range potential as a function of hyperradius, and then start to work with it. The easy thing is like you just like put two potentials equal to each other. This is from 3D space. This is from 6D. But the tricky point here is that because of our definitions for the position vector, these relative distances Rij are both function of hyperradius and hyperangles. And we don't want hyperangles be there. To get rid of them, we do like randomly generating, we randomly generate these hyperangles and then find the distribution for the hyperradius by solving this equation. And this distribution is really interesting, it's called the generalized extreme value distribution, which, yeah, I don't want to speak about this, but it's also really, it has so much things, people are working on it in other areas of science in general. Using this, we just find the row with maximum likelihood and then fit this potential for different rows. And with this, we can find the long-range potential as like the hyperradial part of the long-range potential, with this beta being the power of rho in this 6D space. Okay, now we have our potential. Now what we can do with it, which brings me to the result part. We look at the power we basically look at different intervals of C6 and C4, which are from these two-body reactions. And we characterize our three-body recombination based on this power dependence of this, like a kind of effective potential, long-range potential that we found. And you see here, you can identify three different regimes. Like there is like a regime here more for like a dark side is for beta equal to -4. And then we have another extreme is for beta equals to -6, which is like this yellowish side here. And then beta equals to -5 is for the kind of intermediate regime. What I want to look is like looking at the ratio of these products of my three-body recombination. As I said, I look at both molecular ion and also molecules. And this is the things I want to look at it by, consider this by looking at the opacity function. That's the probability of the formation of these products. And the temperatures we are looking at relatively low 1 millikelvin, which I don't know, I think, okay, it's a cold temperature somehow. Yeah, here you see in the regime that beta is equal to -4, the formation of molecular ion is by far dominating. You basically don't have the K3 will be the integral of under these curves. We basically don't have any neutral molecules to form. But if we look at the other extreme limit, we see that it's actually competing the formation of neutral molecules, and for some impact parameters close to 0, which is like these head-to-head collisions, it's either like overcoming the formation of the molecular ion. If we look at the intermediate regime, we see, okay, still molecular ion is the dominant product, but we should consider also that there are some neutral molecules that they are like, we cannot neglect it anymore. And this was for 1 millikelvin, as I said. Then to summarize, this is like a kind of cartoon that we say, okay, if we are in this regime, the only channel we should look at it is like formation of molecular ion, and if we are in these two regimes, we should consider both channels, basically. Another things that we can use our potential for it is to develop a kind of classical threshold law in this 6-dimensional space. Here you see the centrifugal term. Here this lambda is a kind of grand angular momentum, which is like the angular momentum in 6D space, and the classical definition is a wedge product of the 6D position and momentum vectors. It's the same as what we have in 3D also. And we use this classical threshold, which is like when the collision energy is equal to the centrifugal barrier. This rho 0 is the position of the hyperradius of the maximum of the potential, effective potential. And also we use the conservation of angular momentum, which is related to collision energy and impact parameter. And finally, we can find a kind of this threshold impact parameter, which I'm calling it B max, as a function of collision energy. And with this, following the same method as Langevin, we use that, okay, for B smaller than this impact B max, we have the product with probability of 1, and if we are with the impact parameters more than this Bmax, it's 0. And then we can calculate the geometrical cross-section or Langevin cross-section from this formula. And it's like, and you see, unlike the 2D reactions, this two-body reactions, these are like power of, like they are dependent on the collision energy. And this is my last slide. This is a part of like something that we are already doing. Actually, this it wasn't calculated for this. We were doing it for another project, but we can see things in it because of that is nice. These are the rates, like the blue ones are, the example is rubidium, ytterbium plus, the potentials are from these references. These blue dots are the recombination rates, three-body recombination rates for molecular ion, and the red ones are for the neutral molecules. As the first thing we see in this plot is that there are two power law behaviors, which is like a kind of that is distinguishable by using the dissociation or the Bell depths of these potentials. As you see, like this blue one is following one power law, and then when it's passing, like it's deviating from that and is doing like dropping. Also for the red one, there are something is like going on here, but basically the main thing is also close because the dissociation energies are close. It's happening for both. If this line here, this the dashed black line, EC minus A, this is coming from the threshold law that I showed you in the previous slide. This is for beta equal to -4. And as you see, it's working pretty well for low temperatures, like this 100 microkelvin, yeah, and then we are going to 100,000 Kelvin. For like this regime, it's like giving us a good rates. But then we go to higher energies, this start to deviate. And then the mass deviation happens when we pass this dissociation energy. If I want to, the phase diagram I was showing you, like with all these opacity functions, was related to this 1 millikelvin before. And you see here we have the C6 and C4 related to these potentials are in the regime that beta equal to -4 is dominating. Because of that, you see this, we said that molecular ion is dominating. Because of that, basically with 4 order of magnitude difference between two products, we can neglect formation of the neutral molecules completely. But when we go to higher temperatures, then neutral molecules start to like produce more. And then the rates, the K3 that we calculated in our threshold law was the sum of both products. This was like, we couldn't say which channel is giving this product. And then it's like when we have both products, then of course, when the neutral molecules are getting more important, then the formation of molecular ion is deviating from the threshold law that we, like the power law that we calculated. With this, like we somehow can then say, okay, we can deviate these two different regimes. Like we have high energy regime, which is like the collision energy is more larger than the dissociation energy, and the low energy regime, which is the energy is lower than this energy. And this is like, it's as we expected, this is like domination of the long range potential and all these things that we calculated. We see that is working here. I mean, even with deviation here, but it still is a good, I would say, agreement with the behavior of the rates. Yeah, and with this, I'm like, it's finished on time. Yeah, this is the summary. I don't go to read it, but yeah, these are the take-home points. And then thank you for your attention.
So thank you very much, Marjan, for the nice talk and being right on time.
Yes.
So we have plenty of time for questions. Please, Olivier.
Thank you for your nice talk. Two brief questions. One, you partially answered to one of them. I suspect that when you consider, let's say, the usual system like alkalis and alkaline earth ions, in the graph where you have this competition between C4 and C5, you always are in the dominant C4 regime, right? The C6 is almost always negligible. You would agree with that?
Yes.
Okay, good. And the other thing that I wanted to, your last graph, I mean, you talk about this high energy regime, but I suspect that when you go to high energy, those molecules that you are creating, they will be immediately destroyed by further collisions, right? Because, you know, they are weakly bound. And so given the amount of energy, then immediately they will be killed. So you will never see them, actually. Is it the correct vision, or?
I mean, I'm theorist. I'm naive a bit about like things that what you can see, but I mean, you still, I know it's really low, but still there is a rate of at least we can calculate this rate. But of course, afterwards, maybe they de-excite or they have another collision.
But you don't take that into account.
No,
in your model,
no.
right?
We just look at if these three have happened.
Yeah,
and what
but then
happened.
with that kind of energy, those things, they will not have just time to relax and so on, so they will be killed. So I suspect that this regime will be very difficult to see anyway, because there are so many processes which will take place then. Yeah. So this is why I think it is secure in that sense, in that range, in the low energy range. But here I would be a bit more skeptical.
I agree. And it was like, for example, when we did it for ozone formation, there is like this high energy regime, and there we consider this vibrational quenching. And with that, we could get the right rate for the experiment. If you just go with the three-body recombination, you get things that you don't see in experiment. Yeah, this is true. For cold temperatures, I don't know if you can say, I mean, this is really 10 to the power 4. Okay. I don't know if people look at it in the
Okay. Thank you very much.
Very nice talk. Thank you very much. Did you search for other species where this beta equal to -4 was not dominant, following the question of Olivia?
I did with for strontium, cesium plus, and I think something else. Also, I don't remember, because for lithium, ytterbium plus, I have so much problem. The rates are really bad because this molecular formation, it's so expensive if you want to do it with even classically. We don't do. But for them, yes, in work. Time consuming. Like, but then, but for cesium, rubidium plus, I'm sorry, strontium plus cesium, at least I can say it's exactly the same behavior as you see same. But one thing I forgot to say, it was like in this diagram I showed this formation of the molecules, we changed for different, because it was artificial, and then we changed the short range potential, like the place of minima and everything. It's not affecting it. It's like all this long range. This just was a point I forgot.
All right. Are there any more questions? If not, let's thank Marjan again.
Thank you.